Relation between effective aperture and beam area. Consider an antenna with effective aperture AE which radiates all its power in a conical pattern of beam area then the field at this point is EA. Beam is radiated to some point with the distance r, then field at this point is ER. Suppose that the receiving antenna is a rectangular electromagnetic horn immersed in the field of a uniform plane E. If the horn extracts all the power from the wave over its entire physical aperture, then the total power P absorbed from the wave is given by P is equal to E square divided by intrinsic impedance into physical aperture, or I can denote this as S. Pointing vector is E square divided by Z naught into A, physical aperture. Assuming a uniform field EA over the aperture, then the power radiated P is equal to S into EA, which is equal to, when the field is EA, then S is EA square divided by Z naught and AE. Equation 1. Assuming uniform field ER in the far field at a distance R, the power radiated is given by P equal to S into A, so which is equal to radiated power in the far field at a distance R is given by ER square divided by Z naught, then aperture in the far field at a distance R is R square into omega A, that is beam area. Equation 2. Substitute ER equal to EA into AE divided by R lambda in equation 2. So what is the equation 2? It's a radiated power in the far field at a distance R is ER square divided by Z naught into r square beam area. When I substitute the above ER equation, ER equation, EA square AE square divided by R square lambda square into Z naught multiplied with R square and beam area. When I simplify this, the remained terms are EA square AE square divided by lambda square Z naught into beam area. This is equation 3. Equating equations 1 and 3 is given by equation 1 is EA square divided by Z naught into AE, which is equal to equation 3 is EA square AE square divided by lambda square into Z naught beam area. When I simplify the above equation, I will get 1 is equal to AE divided by lambda square into beam area. Or I can write this equation as AE equal to lambda square divided by beam area. So effective aperture is inversely proportional to the beam area. Relation between effective aperture and directivity of lambda by 2 dipole antenna. Consider the dipole antenna. The distance lambda by 2. Placed in 3 spherical coordinates. Resistor in the antenna RT and current I. Equivalent circuit is dV, small change in voltage, and this is A. Okay. A plane wave incident on the antenna is traveling in the negative x direction. The wave is linearly polarized with field E in y direction. The equivalent circuit is shown here. The antenna is replaced by equivalent generator. Antenna is replaced by equivalent generator. The infinitesimal voltage dV of this generator due to the voltage induced by the incident wave in an infinitesimal element of length dy of an antenna is dV equal to E into dy cos 2 pi y divided by lambda. Therefore, the total induced voltage V is given by E cos 2 pi y divided by lambda dy from 0 to lambda by 2. Induced voltage V is equal to 2 into 0 to lambda by 4 E cos 2 pi y by lambda into dy, which is equal to 2 E integration of cos 2 pi y by lambda is sin 2 pi y by lambda divided by 2 pi by lambda limit 0 to lambda by 4. Therefore, induced voltage V is equal to 2E divided by 2 pi by lambda sin 2 pi by lambda into lambda by 4 minus sin 0. So, V is equal to 2E into lambda by 2 pi, which is equal to E lambda pi. Equation 2. Maximum effective aperture is given by V square divided by 4 SRR. We have induced voltage V, that is, just now we have got the answer, that is E lambda by pi. Radiation resistance of lambda by 2 dipole antenna is 73 ohm. Then radiation resistance of lambda by 2 dipole antenna is 73 ohm. And what is the Poynting vector? Poynting vector is equal to E square divided by intrinsic impedance, that is equal to E square divided by 125. So now substitute V, RR, radiation resistance and Poynting vector S in maximum effective aperture equation, that is V square divided by 4SRR, which is equal to V square is E lambda by pi, that's why E square lambda square divided by pi square into 4 into S is E square divided by 120 pi multiplied with the 73 ohm resistance, radiation resistance. Therefore, A maximum effective aperture is equal to 0.13 lambda square. We know that directivity is equal to 4 pi divided by lambda square into AV. If I want to substitute effective aperture AE, then directivity for lambda by 2 dipole antenna is 1.63. Relation between effective aperture and directivity of short dipole. Consider the short dipole. With length L. The radiation resistance RR, current I. A plane wave is incident on a short dipole. The wave is assumed to be linearly polarized with electric field E in y direction. We know that maximum effective aperture is equal to V square divided by 4SRR. Induced voltage V is product of effective electric field intensity and its length. Induced voltage is the product of field intensity and its length. Radiation resistance of short dipole is 80 pi square L by lambda square. Power density of incident wave at the dipole is related to the field intensity is given by E square divided by Z naught. Now substitute equations 2, 3 and 4 in equation 1, then we get AE is equal to V square divided by 4 SRR. So V is E into L, that's why E square L square divided by 4. S is E square divided by intrinsic impedance, that is 120 pi. Our radiation resistance of short dipole is 80 pi square L square divided by lambda square. It is equal to 3 lambda square divided by 8 pi, which is equal to 0.119 lambda square. So effective aperture of short dipole is 0.119 lambda square, and we know that directivity is equal to 4 pi AE divided by lambda square. When I substitute AE, effective aperture of the short dipole, in the directivity equation, it's 0.119 lambda square, I'll get the answer 1.5. Relation between effective aperture and effective height. For an antenna of radiation resistance matched to load, then power delivered to load is P is equal to V square divided by 4 RR. In terms of effective aperture, power is given by S into A, which is equal to, we know that S is E square divided by Z naught into A. Equating equations, one and two, V square divided by 4 RR, which is equal to A square by Z naught into A. We know that effective height is the ratio of induced voltage to the field intensity. Therefore, V equal to HE into E. Substitute the induced voltage in equation 3, then equation 3 becomes one by 4 HE square E square divided by RR which is equal to E square divided by Z naught into AE. Therefore, AE is equal to HE square into Z naught divided by 4 RR. So, effective height HE square is equal to AE 4 RR divided by Z naught. Therefore, effective height is equal to 2 into root of AE RR divided by Z naught.